Technology and engineering education has only in the past few years risen to the national status that pure sciences have traditionally enjoyed. But in Massachusetts, we're heading the pack. Of course, WPI has been in the business of technology education since 1865, I think. But state K through 12 standards now include concepts in engineering and technology as well. The Museum of Science is also in the midst of this tech initiative, and we'll be celebrating National Engineers Week on February 21st with a Zoom into Engineering event, as well as looking at sports engineering and aerodynamics on February the 2nd, which is a Friday evening lecture. We'd also at this point like to thank the Lowell Institute, which if you come and see lectures here at the Museum of Science, you've heard that name every single time, I'm sure. But they fund and support a lot of the programs that we do here, and they make sure that you can attend events such as this one here and across Boston for free. So thank you very much to the Lowells. Tonight's lecture is The Hydrogen-Based Economy, Dream or Reality. If you'd like to revisit this lecture or you missed the previous two lectures, you can see the video footage online. We haven't gotten up there quite yet, but visit the Museum of Science website in about a week or so, and you'll be able to see all three lectures via streaming video. And the addresses for the Museum of Science website, it's also going to be up on the WPI website, as well as the WGBH Forum Network website. Those three sites are on your red lecture summary sheets, pardon me, those red ones that you picked up at the front desk. Finally, I have the pleasure of reintroducing our series moderator, Dr. William K. Durgin, who's the Associate Provost of Academic Affairs, the Vice President for Research and Professor of Mechanical Engineering at WPI. Professor Durgin is active in several professional organizations, including acting as Fellow of the American Society of Mechanical Engineers and Associate Fellow of the American Institute of Aeronautics and Astronautics. So as you can see, we're very fortunate to welcome back to the Museum of Science Dr. William Durgin.
Well, thank you, Caroline. Wonderful beginning as always. Before I go any further, I just want to say thanks to the Museum of Science for providing this opportunity to WPI and for all of you. This is truly a great occasion for all of us to get together and explore some issues in engineering and science. So it's a terrific opportunity, and thanks to the museum. Good evening, everyone. I see alumni of WPI here. I see colleagues, I see friends, I see students. This is a wonderful group of folks to have together here this evening, and we're going to explore a particularly interesting topic. This is the third lecture in the series, as Caroline mentioned, and it's the final one of this series. We were here 3 years ago. We'll probably be back again and do another series in another 2 or 3 years, but it's great fun for us, and it's a good chance for WPI folks to interact very strongly with all of you folks from the greater Boston area. So this is a great opportunity for all of us. Tonight we have a particularly timely topic. We all use energy copiously every day of our lives. Many of you probably drove here using gasoline to power your cars. You've probably been burning lots of oil or gas in your homes to stay warm these days. And the electricity that we're using here is generated in some power station in the immediate area of New England by burning either coal, oil, or natural gas to produce electricity, which is shipped to us by power lines, and we use it. And the problem, of course, with this type of energy, or at least two of the problems with this type of energy, have to do with the fact that there are environmental consequences of burning these types of fuels and to produce the energy that we all need. The other problem with most of these energy sources is that they're converted to useful forms with fairly low efficiency. So we really don't get all of the value of energy that's available in these fuels and have to throw a lot of it away in one form or another. So, what we'd like to do is we'd like to have a fuel and an energy stream that's non-polluting, doesn't affect the environment very much, and that gets converted to the form of energy that we need, or the forms of energy we need, at very high efficiencies. Well, it turns out that hydrogen is very, very attractive from that point of view. One of the advantages is, and you'll see some demonstrations here later, is that if you put some hydrogen into a device with some oxygen, you get electricity out. and the conversion rate is quite high. The efficiency of those devices can be quite high. So we'd like to explore that particular energy stream a little bit tonight, and that's our purpose. The conversion device is called the fuel cell. And we're going to spend some time talking about how one goes about doing this tonight. Now, of course, oxygen is not a problem. We're immersed in a sea of oxygen as we stand here. So to power that half of the fuel cell is easy. We just put air into it. But the real question is, where do we get the hydrogen? Now, it would be real convenient if we just went down to the power station and used electricity to break down water and make some hydrogen and ship it up here and put it in the fuel cell. But that just adds complexity and further inefficiency into the system, and so clearly we're not going to be able to justify doing that, and probably wouldn't want to do so economically. But the question is, just how are we going to make this hydrogen that we need? So tonight we're going to talk about three things. We're going to talk about how we might produce hydrogen. And then we're going to talk about how we might convert hydrogen and oxygen to an energy form that we can use. And finally, we're going to talk about some very interesting applications of those systems. So we're going to hear from three folks tonight. First, we're going to hear from Professor Ed Ma. Ed holds the Francis B. Manning Chair of Chemical Engineering at WPI. Previously, Ed was the head of our Chemical Engineering Department. He earned the PhD at MIT and is the director of our Center for Inorganic Membrane Studies. Ed invented the technology that will probably be used to manufacture hydrogen from natural gas. So we've got a very special guy here tonight to tell us about that particular process. Then we're going to hear from Professor Ravindra Datta. Ravi earned the PhD at UC Santa Barbara. He's the current head of our Chemical Engineering Department, and he's the director of our Fuel Cell Center at WPI. So another person who knows an awful lot about this subject. Finally, we're going to hear from Mr. Jim Dunn. Jim's an alumnus of WPI. He's the CEO of the Center for Technology Commercialization. He's the director of NASA's Regional Technology Transfer Center. He's the co-founder of WPI's Venture Forum. He's worked for IBM and Exxon, among other companies. He's been a consultant to the National Security Agency, and he served in the U.S. Navy Security Group during the Vietnam conflict, and he's an expert, as you might expect, in cryptography, software, and communications. He holds a number of patents on the original design of the laptop computer, and he's the executive director of the Foundation for Advancing Science and Technology Education. So we've got a real resource and a marvelous opportunity to hear from Jim tonight. In simple terms, Ed Ma is going to tell us about how to produce hydrogen. Ravindra Datta is going to tell us how to convert that hydrogen into electricity, and Jim is going to tell us about systems that can use that hydrogen and the electricity that we produce. Now, as we go through this lecture series tonight, I'm going to ask each of these three folks to make their presentation. During that time, I want you all to think of really good questions to ask them, because once Jim finishes, the final of the three speakers, we're going to engage in what I hope will be a pretty lively discussion. After we have some discussion, we'll probably excuse anybody who wants to leave and invite anybody that wants to stay and come down and chat with the presenters to do so. So with that, Ed, I'd like to give you the podium.
Thank you, Bill. I would like also to thank all of you who come here under the weather like we have. I was worried that I couldn't make it. Well, tonight I would like to give you first some overview of the hydrogen, how we make hydrogen. And I have spent most of the time to talk about the technology we are working on at WPI, and I hope that technology will help us to get to the hydrogen economy as soon as possible. This one, okay. The title of tonight's talk is Hydrogen Production. Now, if we look at what President Bush in his 2003 State of Union speech, he mentioned several goals. One of the goals, his third goal, is to promote energy independence for our country while dramatically improving the environment. If you look at this, there are two key points here. This development will be through technology and innovation, and also he will provide some funding for doing that. Now, if we look at that, we'll see that hydrogen, as Provost Durgin said, well, it's easy. You took water, put energy in, and you get hydrogen and oxygen, and then you store the hydrogen and go to fuel cell and all kind of energy so you can use it. However, this is really a difficult, easy thing to do, but it's very expensive to do that. Now, currently, all the hydrogen are produced through fossil fuel. So, if we talk about current hydrogen economy, we still cannot get rid of this problem here, the greenhouse CO2. Now, if we are going to spend a little bit more time to talk about this fuel processor to make hydrogen. Now, once you make the hydrogen, you can store the hydrogen. This is another big problem there, how you store hydrogen. Or you can take this hydrogen directly feed to the fuel cell to generate energy. Now, if we look at that, I'm showing here a graph is transition from current technology to hydrogen economy. Now, if you look at this as a product performance versus time, we start with coal. Now, coal here, under here, we say coal is about 1.5 carbon to 1 hydrogen, 1.5 to 1 to 1 hydrogen. And then you move up to oil. In oil, you have 1 coal to 2 hydrogen. The gas, natural gas, is 1 carbon, 4 hydrogen, which means now you can produce hydrogen the least amount of CO2 to be produced. Now, when you go to hydrogen economy, now you got no carbon, so you, as Provost Durgin said, now you combine hydrogen with oxygen, give you the water. So that's your byproduct of your energy. So this is really environmentally benign product. Now, if we look at that now, currently we are in this stage here, the transition. The transition is very uncertain, simply because we have to find a good way to make hydrogen. A good way means we need an economic way and also an efficient way to do that. Let's look at the next slide, we'll show you. Now, if you look at the water, well, the best way to do that is to take solar energy to do electrolysis of water, then that's the best way you do it. But that's really a long way to go. In this case, the hydrogen to carbon ratio is 1:0, or there was some suggestion is to use nuclear energy to electrolysis of water. As we all know, there are other problems associated with that. Again, this is the best way to do it, but it's not the most economic way of doing it. Again, here you don't produce any greenhouse effect. Now, the next thing is fossil fuel. Well, natural gas, as I said before, is 4:1. Now, currently, most hydrogen used in chemical industry or petrochemical are produced through natural gas, what we call steam reforming of natural gas, and I'll talk a little bit more in a few minutes. Now, this is what we call hydrogen produced by steam reforming of methane. What you do is, if you look at this one first, you combine methane with steam. Actually, you use steam, you have two hydrogen here also, so that you take the hydrogen from water this way. So methane and the steam give you CO2 and hydrogen. Okay. Now, this is what we call overall reaction. In fact, there are two reactions taking place in this kind of process. First one is methane react with water to form CO and hydrogen, and the CO and the water react again to form CO2 and H2. Now this is called water-gas shift reaction. Now this reaction actually is the trouble for the whole system here, because this reaction is generally controlled by thermodynamic equilibrium. So in the case here, so no matter what you do, at one temperature, you can only convert that much of methane because you control the thermodynamic equilibrium. So what we want to do is to be able to increase the conversion, what people used to call shift equilibrium. Well, thermodynamic cannot be shifted, but you can increase the conversion by doing certain things. And that's what we're going to talk about, how we do that. Here now I'm showing you that a simple fuel processor. Now this is essentially for a fuel processor to be used in fuel cell system, but essentially in industry you use the similar type of process. Doing that, you have a reformer here, and then as I said, that the water-gas shift reaction, it's very difficult to promote that, so you do high temperature shift reactor and low temperature shift reactor. And also then what's left over of CO, you want to oxidize it to become CO2, and then you separate to pure hydrogen. Now sometime in the fuel cell, you don't need the pure hydrogen. You can go this here directly, go to fuel cell. Now what we are doing in WPI is to use what we developed a certain membrane which can be used to make this hydrogen. And in that case, what we call the membrane reactor, we replace this whole 5 unit operations by a single reformer, which means now you save all this process here, and equipment-wise you are cheaper, and also operation-wise because you have less unit to worry about it, so that become more economical and efficient way of doing it. So what is a membrane? For some of you may not be familiar with membrane. Here is, I have the membrane here for you to see, and this is 2 of them. This one is what we call support, and that we put our membrane on this support here, and this one has a membrane inside. When we finish, if you want to come up to look at that, you're welcome to come out to look at that. And if you look at that, this is the tube I show here, is this tube here. And this end is a non-porous stainless steel tube. And that's also non-porous stainless steel tube. In the middle portion of this is a porous stainless steel. In simple term is the stainless steel tube in the middle is porous like a sponge. Okay. Now outside the sponge, we're going to put a layer on top of that. That we put a palladium or palladium alloy membrane. And I'll explain why we put that on. Now, in this unit here, generally you do is you have a gas mixture come in here, and gas mixture goes out here, and hydrogen go out here. So what happens is you have the mixture of gas coming in, hydrogen going through here. This membrane only allows hydrogen to go through. So pure hydrogen go through here and go out here. You can collect that, go to the storage, or go direct to a fuel cell. Now that's a very simple process. At the end, I'll show you a comparison between this process versus currently commercially available unit. Well, what we do here is we look at that. We say, well, we're going to put a very thin palladium or palladium alloy on here. And we use the advantage of doing this thing is metal support, which means now it's very easy to connect to different part of the process. And also they have very good mechanical strength, of course, chemical and thermal stability, and not very fragile. And because you have 2 metal put together, you need, when you run these reactions, are very high temperature. So you need some similar coefficient of thermal expansion. And we can easily form the module and can easily integrate to the process. We do electrolysis plating. What is electrolysis plating? We all know electroplating. You pass electricity to place something some elements on top of a support of a surface. Electroless plating is we do not use any electricity to plate. Sometimes it's called chemical plating. What it means is we use certain kind of chemicals. We activate the surface first, and then we see some of the nuclei on the surface, and then we carry out the reaction, become autocatalytic. The reaction will take place by itself and to coat the material. That, again, is really easy to do, and also we can coat it very uniformly. When you look at the sample, you see that. And the film we do is very hard and also get a very good adhesion between the coated film and the support here. And a very simple equipment for doing that. Here's the process we do, and I'm not going to go through that, just to show you this process we're going through. We have to clean the surface, we have to sensitize the surface, and then we see some nuclei, and then we plate it. We have to do it several times to get this process, to get the membrane we need. The important part is this one. That's the WPI hold this pattern on this procedure here. What we have here is, because we are making two metal contact together, what it takes when you have high temperature, when two metal get together, one metal will diffuse over to the other metal. So in order to avoid that, we create a layer as a diffusion barrier, so that the metal elements will not go into the membrane, which will deteriorate the membrane. And this is where this process, unique process of that. Now, if we look at that, this is the surface of the membrane, and this is the support, and this is the palladium on the surface here. This is the cross-section of the membrane. If you look at the next one, you look at the surface of the membrane. These are clusters of palladium, and at different magnification. If you look at this is the highest magnification, you see here, these are clusters, and also inside the cluster are the small grains. And hydrogen will diffuse through these layers of metal. Here's I'll show you that. This is the palladium membrane, which I showed before. And we have high pressure side here, low pressure sides here. When hydrogen come over, it will come to the surface and will decompose. It will dissociate to two atoms. Hydrogen molecules come to the surface, dissociate to two atoms, and will move through the palladium layer, and then go to that next side, the other side of the membrane, and then recombine to hydrogen molecule, and then dissolve from the membrane. So this is the process taking place. When you have the hydrogen, it will absorb on the surface, dissociate on the surface, going through this membrane, and reassociate to give you the hydrogen gas here. Now, if you go through the analysis, you get this, what we call the flux, which is essentially how much hydrogen can go through per unit area of the membrane. And it's proportional to the pressure, square root of the pressure difference, and also it's inversely proportional to the thickness of the membrane. So we want to make the membrane as thin as possible, but still, as what we call dense, but still will not allow any other gas to go through. Here are some of the data we have. Now, what I want to show is this is permeance essentially is the flux of the membrane versus 1 over the thickness of the membrane. As the previous slide shows, that if you have thinner membrane, it should give you higher flux. This is thinner membrane here. And what I want to show you is this is the DOE's near-term target. Our technology right now already exceeds current DOE's near-term target. So that's why this technology is quite unique. That's what Provost Durgin mentioned about that. That's very, very unique in the sense of we can satisfy we exceed DOE near-term target for hydrogen production here. Now, just to show you pictures, we can make small one, like this one about 10 inch and about 1 inch diameter, and this one about 12 inch. And the next one we'll show you is this one. And you can see that these are two of my associates. They all have to be 6 feet tall all over because that's so long here. And one of my friends said that it's not the membrane is long, it's because Professor Ma is short. And one of the things we have to worry about is how stable is this type of membrane under high temperature. Here we show one of the membrane we made. The time here, the flux here as a function of time here, you can see this is about 500 hours. We run that 500. Now, certain membrane, we run it over several thousand hours because industrially you need at least a year or 2 year life in order to make industrially applicable. Simply, you need that to make economical process. Now, as I said, we look at this type of membrane. I'll show you one more here is alloy membranes. This is palladium and copper alloy. Now, why we do palladium and copper? Well, certain fossil fuel contains sulfur. And palladium, sulfur is not very good for palladium, but palladium copper alloy can resist the sulfur. So we also make this type of membrane, as you can see. And also we need to be concerned about, as I said before, the intermetallic diffusion. In other words, that the material elements in one membrane, in the support, diffuse into the membrane itself, okay, to the membranes. And we have EDX data to show there's no element in the support go into the membrane, which means that this barrier layer we made, or the pattern we hold on the barrier layer is effective in terms of avoiding this type of problem happening. Now that's what I want to show you is, this is what we envision as our reformer. Okay, this reformer here has the tube here are the membrane tube I have described to you before, and these are catalysts. The steam reforming process needs a catalytic reaction taking place. So these are the catalysts, and if you have methane and a steam passing through here, and this is a heater. The heater here is called a flameless distributed combustion. We have a very, very extensive program with Shell Exploration and Production International, Inc. Now, Shell International, this is a part of Shell Hydrogen, and they have developed a technology where you can directly put heat into the system. When you do this type of reaction, because they require high temperature, 500 degrees or above, and it's very difficult to put the heat in. If you put the heat from outside, then you have to heat very hot so that these units here become, the material for construction become very expensive. By doing this type of heating, you directly go into the system, and the surface temperature now is around 600 degrees centigrade rather than, say, 1,000 or over this way. Now, if you look at the methane and the steam going into here, and the CO2 go out here, and hydrogen come out here. Now, one of the advantages of this system here also is when you do this, because this reaction is run at high pressure. So CO2 stay here. This CO2 is high pressure CO2. Why do we want high pressure CO2? Well, one way to deal with the CO2 problem is to put CO2 somewhere, sequestration of CO2. in order to do that, you require very high pressure CO2. So in this process, you do not have to pressurize the CO2 for storage CO2, for example, in the ocean or for oil, for tertiary oil recovery. Now, here I have a unit here. This is from hydrogen source. This is a 5 kilowatt unit of produced hydrogen enough for a 5 kilowatt fuel cell. Now, if you look at that, 1, 2, 3, and one more 4. In this process, they use catalytic partial oxidation units. Okay, so they have 4 here, but this one does not produce pure hydrogen. So they don't have a separator. So you have 5 unit here. If you use this one, then all you need is this one to replace 1, 2, 3, 4 here. So that's really the advantage of this process we're talking about here, that you can do it with a simple unit here, and also at the same time you get the caveat of you can put the CO2 away. And also you come out with CO8 hydrogen here almost 99 or 99.9% purity here. So this is what the process we're talking about, and we hope that process will be available in the short future. Now, here's some of the data to show this is run by Shell, and that's in one of their patent application, and use our membrane, this one, and to show how high the conversion, how high purity the hydrogen you can get. At 95%, you can convert 93 to 99% of methane, which means the conversion itself is very, very, very high here. Again, that's a steam reforming reaction here. Now, let me conclude my presentation to say, well, electrolysis of water certainly is the cleanest way for hydrogen production. However, technical and economical challenge remain to be resolved here. Now, transition from fossil fuel to hydrogen economy is uncertain, and considerably R&D still required. And development palladium membrane reactor for more efficient economical hydrogen production with simultaneous CO2 sequestration. Now, that's the important part of this process here. Not only we can produce pure hydrogen, at the same time we can solve part of the CO2 problem. I say part of it because we still produce CO2, but we have a relatively easier way to put the CO2 away. So this will provide a cleaner way for near-term hydrogen production. I believe conservation is probably one of the best way to solve some our long-term energy problem and to make us self-sufficient and keep our environment clean. I need to acknowledge the people who provide fundings, this whole development. Currently, this is supported by Shell International Exploration and Production in Houston, Texas, and also the people who did all the work. Here's other people who did the work. We have probably one of the largest palladium membrane group in the U.S., if not in the world. Thank you very much for your attention.
Professor Ma described some of the latest advances in the production of hydrogen, which is really the fuel for fuel cells, and he mentioned that the excitement about fuel cells stems from the fact that the only product of production of energy in a fuel cell is pure water. Of course, there's carbon dioxide that is produced in the process of producing hydrogen. What I'm going to do is I'm going to give you a brief introduction to PEM fuel cells, or proton-exchange membrane fuel cells. Fuel cells, even though the excitement about fuel cells is relatively recent, fuel cells actually have pretty respectable antiquity. More than 160 years ago, they were developed by Sir William Robert Grove. And what he found, it was known at that time that if you take water and if you have two platinum electrodes, and if you connect them through a source of electricity, that they would produce hydrogen, oxygen and hydrogen. What he argued was that if once you've collected the hydrogen and oxygen, if you remove the power source and if you connect these wires, then it should produce electricity. And he was surprised to find that indeed that was the case. What I'm going to do is, if someone can turn on the light at that table, as I go along, I'm also going to give, this is a very sort of a basic introduction to fuel cells. I'm not going to go into a lot of technical details, but I do want to, for those of you who are uninitiated in fuel cells, to show you how it works. So the first thing that I'm going to demonstrate is electrolysis. Here is a beaker in which there are two electrodes, and these electrodes, I don't know if you can see them or not, but these foils are platinum. And what I'm going to do is, it's already connected to a cell, and I'm going to put some water in this to see if there is any electrolysis. Well, I don't know if you can see or not, but you see that there are no bubbles. So what do you think is missing in this? Pardon? Electrolyte, yeah, that's exactly right. What is missing is that you need an electrolyte, and in this case there's a very dilute sulfuric acid solution, so which I'm going to add to it to see if the electrolysis begins. Nothing. So I've added a little bit of sulfuric acid, and I don't know if you can see the electrodes, but you can see the bubbles. So I think that illustrates the basic ingredients of a fuel cell. You need two electrodes, you need an anode and a cathode. This is actually just the reverse process of fuel cell. It's the, so you're using electricity to produce hydrogen and oxygen, whereas in a fuel cell, you use the reverse process. And you might be able to see that there are bubbles of hydrogen and oxygen on the electrodes. So I'll fast forward to the modern fuel cell. In the modern fuel cell, you have an electrolyte, which is the membrane. So there is no liquid electrolyte. And so this whole thing is a solid state device, and I'll show you an example of that in a minute. But the hydrogen comes in. This is the hydrogen molecule that comes in. There is platinum that is dispersed on the surface of the membrane in a very, very distributed form, so that you can utilize the platinum very effectively. But the hydrogen molecule breaks up into hydrogen atoms, and it strips off the electron because the electrolyte does not allow the electrons to go through. The electrons are forbidden to go through the membrane, so they go through the external circuit where they perform some useful work. They arrive at the cathode, where they meet up with oxygen, So the oxygen molecule also dissociates into oxygen atoms, and it combines with two hydrogen atoms and two electrons to form water. So water is the only product. So this is the reaction that goes on at the anode, where a hydrogen molecule forms two protons and two electrons. And at the cathode, you have half a molecule of oxygen combining with two protons that come through and two electrons that come through the outer circuit to form water. So if you look at the overall reaction, which is just the combustion of hydrogen, and because this happens at a low temperature, at around 80 degrees or so, it's called cold combustion, because the overall reaction is the same as combustion, and I'll give you another demonstration of that. You combine hydrogen and oxygen and you form water, but you don't do it at high temperature. So let me just show you the second part of the demonstration. So I have here a tank of hydrogen, compressed hydrogen, and a tank of oxygen. You don't need a tank of oxygen. You can use air. What I'm going to do is, so I've already opened the valves, and I've been bypassing it. So what I'm going to do is I'm going to mix the two, and it's going to come out of this nozzle here. Okay. To show that there is a gas flow, I will. There's a soap solution here that makes a bubble. So can you see the bubble? Okay. Now, I'd like you to look at the bubble. It has hydrogen and oxygen in stoichiometric proportion, but nothing is happening. It's not combining to form water. So what is missing? We saw in this example that what was missing was the electrolyte. What's missing in this case? Activation, yeah. So you require some energy to activate it, and that energy can be provided either as a spark or as a catalyst. Catalyst does not provide the energy, but it lowers the activation energy. So let's see what happens when I use catalyst. So I'm going to make another bubble. Now here is platinum catalyst. It's not a foil. It's dispersed. It's platinum black. So it's a powder of platinum. There is $100 worth of platinum here. So I want to be careful. But what I'll do is I'll take a Q-tip, and I will pick up some platinum powder, and let me apply it to this bubble. So you see that. That's the other ingredient that was missing, is the catalyst. So I'm going to shut this off. Actually, I have another part of it. I'm sorry. Before I go on. So we saw in this that you need an electrolyte, you need platinum, and of course the platinum is extremely expensive and you want to disperse it as finely as you can, and that is one of the things that chemical engineers have accomplished, that we can disperse this catalyst in such a fine way that you use very little of it. And an example of that is the catalytic converter in an automobile that costs only a couple of $100, but it's based on platinum. And so it has very little platinum in it. Now, the second part of this demonstration is the fuel cell. The fuel cell, there's a single cell, just like a AA battery, but it looks like this. Again, I don't know if you can see this very well or not. This is the membrane, the clear plastic part that looks like a transparency, and these are the electrodes. Between the electrode and the membrane is a very fine layer of platinum, which is the catalyst. And what you do is you put it in the hardware so that you flow hydrogen on one side and oxygen on the other, and it begins to produce current. So if you would, because it's a single cell, it produces less than a volt. All it can do is power this toy motor. So you watch this needle, if you can, as I turn the hydrogen on towards the fuel cell. So it's as simple as that. You turn on hydrogen and it begins to produce electricity. And I haven't even turned on oxygen yet. It stopped for some reason. Okay. And if you could read the current, it's roughly 100 milliamps and about 0.8 volts. Now, what is impressive about this is not the voltage, which is, of course, like a single cell, but the current. That this little device with the active area of 5 centimeters square can produce up to 5 amps of current. And so it has a very high energy density, and that's one of the attractive things about fuel cell. So this is all it is. This is the heart of the fuel cell. And this is a single cell. What you can do is you can stack this together and produce any voltage or any current density that you want. I'm going to turn this off so that, but you'll see that this is going to continue to turn so long as there is some hydrogen in the lines. And at the end of the presentation, I'm going to turn this off. But let me go back to the rest of my slides. So what looked like a pretty simple device is really quite complex technically. And that's the reason that it took so long for it to get to a stage where it's competitive in terms of cost and performance for terrestrial applications, although in spacecraft it's been used for a long time. So this is the membrane, the thin plastic that I showed you. This is the catalyst layer, and that's the electrode. And so the details of the device are such that because you're producing water here and you want oxygen to go through, you want the water to ooze out quickly. You don't want water to block this electrode. So what you do is you make it hydrophobic with Teflon so that oxygen can go through. But you're also collecting current. So this electrode is made from carbon cloth. The catalyst is dispersed on as 5 to 10 nanometer particles on carbon, and you have Nafion solution. So this is Nafion, this membrane. And of course, the protons that are produced here must find their way here. So there is Nafion solution here as well. And the Nafion is shown here. But you also need hydrogen to be able to get to the platinum catalyst. This is the carbon particle support. So you have some Teflon here as well to make it somewhat hydrophobic. So the construction is really quite sophisticated. Here's an example of dispersed platinum, and you can see that the platinum particles are very, very small. In fact, the total platinum loading per centimeter square of the active area is only 4 milligrams per centimeter square. So it's not a lot of platinum. The device that I showed you is put together like this. There is the membrane that you paint the catalyst on either side. There's the gas diffusion backing, gaskets, and you put it together. There are serpentine channels for the flow of hydrogen and oxygen on either side so that it can flow across the electrode. This is the lab setup at WPI where we test these things. And, of course, we design and we try to improve the performance and to make it more susceptible to carbon monoxide poisoning, which is one of the main problems with fuel cells, is that they are highly susceptible to carbon monoxide poisoning. There are a number of things that we work on, and this is an example of a setup. The typical performance curve, as I said, is the open circuit voltage is roughly 1 volt. In fact, the thermodynamic voltage is in excess of 1.2 volts, but the oxygen reaction is so inefficient that there's a large voltage drop here. So this is the current density in milliamps per centimeter square. So you can see that you can easily go up to 1 amp per centimeter square at a voltage of roughly 0.7 volts. So the largest efficiency drop is at the cathode, but there is also resistance of the cell and the anode for the anode reaction. And so the overall performance characteristics of voltage versus the current density is given by this curve here. And of course, if you multiply the voltage by the current density, you get the power density curve, and you can see that it has a power density of roughly 600 milliwatts per centimeter square of that device that I showed you. To make it into, so what I showed you is the single cell, and to make it into a multi-unit cell, this is a single unit in which you have the membrane, you have the electrodes, and these are called the bipolar plates, where hydrogen and oxygen snakes back and forth through these channels on both sides, hydrogen on one side and oxygen on the other. It's called bipolar because the anode for one is the cathode for the adjacent cell. This is an example of a stack assembly. This is 600 watt cell by Manhattan Scientific. And so what you do is all those single cells, you stack them together. You can produce any voltage you want, and depending upon the area, this is circular in design, but depending upon the cross-sectional area, you can produce any current that you want. I'll briefly go over some of the applications. The earliest application was in space. Actually, this is not PEM fuel cell, proton-exchange membrane fuel cell, but these are alkaline fuel cells that were used in the earliest applications. And if you remember Apollo 13, that was the movie, the disaster was centered around the malfunctioning of the fuel cells. So fuel cells have been used for quite a while by NASA. But some of the more terrestrial applications, I guess, are shown here in terms of small-scale applications. It's envisioned anywhere that you can use a battery, you can use a fuel cell. So there's a small fuel cell here. Again, unfortunately, you need a cartridge of hydrogen. And it's this is the fuel cell for a laptop. Again, you need hydrogen. And that's one of the problems that Professor Ma alluded to. For personal transportation from Manhattan Scientific, these pictures show this is a fuel cell powered bike and a scooter. I think this is 600 watts. This is about 3 kilowatts fuel cell. These are all prototypes. You can't buy them. I'm sure you've heard of the Segway, and the latest model has it driven by a 700 watt fuel cell. Incidentally, this, if you know, I'm not sure if you know or not, is developed by Dean Kamen, who went to WPI. Of course, some of the more exciting applications are in automobiles. So here is a prototype for Volkswagen prototype for hydrogen-fueled car. The problem, of course, as Professor Ma described, is where does hydrogen come from? And I've given a schematic here of the reforming process that Professor Ma described in detail, so I won't go over it. But the problem is that for automobiles, this is a GM gasoline reformer. So it takes gasoline, and on board, it can convert it into hydrogen. But it's humongous. You don't see the scale here, but it is mounted on the back of this truck. So it takes up most of the room, and that is part of the problem. That if you want to, before we get to the hydrogen economy, the only fuel, practical fuel that you have is gasoline. So the thing has to run on gasoline. What is done is this is a reformer that converts gasoline. So you drive up to the pump, you fill up on gasoline. This would convert it on board into hydrogen that would be used in fuel cells under the hood. So again, the problem is the size and the complexity of the plant for producing hydrogen. And the technology that Professor Ma is developing at WPI, of course, is very promising in this respect. This is a car that runs on methanol. It's a methanol-powered fuel cell. The reason methanol is attractive is it is a liquid fuel, although it doesn't have energy density as high as gasoline, but it's much easier to reform, and that's the reason that methanol is an attractive fuel. There are also potential applications for home, in which you produce your own fuel cell is located outside. You produce your own electricity, and we use the waste heat. I should have mentioned in the slide that showed efficiency. that the efficiency is typically about 50%, so the rest of it is heat that you can use for boilers and so on, and for heating your home. Let me quickly describe some of the challenges. So the fuel cells themselves, the technology has been a long time coming. As I mentioned, the fuel cells the concept was developed a very, very long time ago. But it's only now that they are becoming cost and performance effective. Even now, there are plenty of challenges that we are working on. For example, the fuel cell that I showed you, it has an operating temperature limit. You can't go above 80 degrees. And the reason is that the membrane conducts protons only when it is soaking in water. So if you go above 80 degrees, of course, it dries up, and it's not going to conduct protons. So even though it is nominally a solid electrolyte in the sense that you don't have a liquid, but you need water in the membrane. So you need 100% relative humidity. It has extremely low carbon monoxide tolerance. As evident here, this is the voltage versus the current density. For pure hydrogen, if you have 25 ppm hydrogen, the performance drops to this. If you have 100 ppm hydrogen, and if you want to operate at 0.7 volts, you can see that the performance drops from 1 amp per centimeter square to 250 milliamps. So 100 ppm of carbon monoxide, and that's the level in cigarette smoke. So it's not a lot. That it essentially kills the performance of the fuel cell, and that's why you need pure hydrogen. Again, it's not the fuel cell that is the problem. It's the I guess it is the problem in the sense that it is not carbon monoxide tolerant, but you need pure hydrogen. I also mentioned the fact that the cathode is very inefficient and accounts for the largest efficiency drop. You need still high platinum loading. If you want to use it in automobiles, you need to be able to produce a 75 kilowatt plant for $3,000 to compete with the internal combustion engine. And you still need to reduce the platinum loading a little bit further. The Nafion membrane is expensive, and there are a number of other issues that need to be worked on. Some of the challenges for hydrogen production, Professor Ma has already alluded to, so I won't go into a lot of detail. But the large size, the weight, and the cumbersome process are some of the challenges. I'm not going to describe what we do at the WPI Fuel Cell Center, but many of these technical challenges are being addressed by undergraduate through graduate students. This is a movie that I hope would work.
A PEM fuel cell is made of a catalyst-coated membrane between two plates. Hydrogen is fed on one side, oxygen on the other. The hydrogen splits into a proton, which goes through the membrane, and an electron, which is captured as useful electricity. The proton and the electron combine with the oxygen, generating water and heat. A fuel cell will operate continuously as long as fuel is supplied.
Thank you.
Now we're going to talk about how we can do some very interesting things with fuel cells. We have several projects that we have undertaken, and we're going to talk about one of the more challenging aspects of trying to find a way to make a fuel cell that's efficient enough and light enough and compact enough to use it to propel an airplane. And in the course of doing this, we looked at first all the different applications, and these are some of the programs that are underway. There's an electric unmanned vehicle called the Helios that NASA has funded that was developed by AeroVironment that has actually flown to 96,000 feet on solar power. When we put the fuel cells on, unfortunately, we only got it to about 3,000 feet before we ran into some problems. It kind of broke apart. That project, though, really has led to a lot of interesting areas, and we'll talk about those more in a second. Boeing over in Madrid is looking at using fuel cells for the auxiliary power on board a jet. And this is because when you sit on the ground, the auxiliary power turbine is running all the time, and in many cases running all the time that you're flying, in addition to the propulsion jets that are flying. But that generates a lot of fumes and a lot of other issues in terms of waste heat and so on. So that's a big application. And that aircraft actually is going to be coming over to the U.S. Sometime in May, and we're going to put some of our drive systems in it that we're developing at WPI and complete the project. Electric airships is another area, and high-altitude airships have some very interesting attributes, particularly if we can get them to stay aloft perpetually and keep them on target and provide enough power to run communications and other things as a replacement for a low Earth orbit satellite. And then electric-propelled aircraft, which is what we're going to talk primarily about tonight, is the ultimate challenge, to have a manned aircraft that runs totally on a fuel cell power. So this is the Helios that we mentioned, and that has a 247-foot wingspan and is powered by 14 electric motors, each of which produces about 3 kilowatts of power. And that wing is so flexible that it can almost bend all the way up and touch the two wingtips. This is an artist rendering of what we could have someday with the return of the airship. And that airship not only has a lot of solar area on it, but has fuel cells as well to get it through the night. And so that could fly basically perpetually. And this is our electric-powered airplane that you'll be hearing more about. So what we are doing with this project is, number one, demonstrating the viability of electric-powered aircraft and determining what is the optimum energy source. How do we get the power to operate the plane? And then, as part of a study that we've done with NASA, we're looking at all the trade-offs involved to get the maximum amount of energy and maximum performance out of a given amount of hydrogen. And then we're actually developing a very special high-performance fuel cell and then integrating it into the airplane. And a lot of this work is being done by students all over the world, a lot of which are right at WPI, even with local schools. And as we alluded to earlier, electric airplanes offer a lot of significant benefits. Of course, in terms of reliability, we only have one moving part. That's the propeller. It's coupled directly to the armature of the motor. And electric motors offer a lot of benefits, particularly very high efficiency. The electric motor we're using in this aircraft is over 90% efficient, including the losses of the controller. Obviously, it's going to be a lot safer, and it's much quieter because we only have propeller noise, which is still significant, but we can spin the propeller at a lower RPM because we produce a lot more torque. And then, of course, the comfort and maintenance issues are important basically to the pilot and the passengers. And the biggest benefit of all is we have no emissions. And the only byproduct we produce is water vapor. The participants in the project is quite a group of people here, and I won't read them all off, but all the components on this project have been donated by various companies that are involved because it's such a breakthrough program. And we have a lot of labor and other assistance being donated by various volunteers and students and even some of the professors and the test pilots too. And how many pilots are in the audience here? Do we have any pilots here? I know we got at least one or two. Okay. Well, the two in the front row we've already signed up. But any others of you that are certified test pilots, come see me later. Our goal in the project is to fly initially all electric, just on nickel metal hydride batteries, to prove out the electric drive system and the controls and be sure everything is working properly before we introduce the other issues of adding the fuel cell. And that's going to be a fairly short range, and you'll see why in a minute. And we hope to do that this spring. Then we're going to add a fuel cell into the system later in the year that will provide just enough power to cruise the airplane, about 20 kilowatts of energy. And with this particular airplane, this will provide a cruise of about 80 to 90 miles an hour. And although the plane will do over 200 miles an hour, it takes quite a bit more power. and we hope to fly that at the end of the year, and that'll give us a range of at least 200 miles. Then we're going to expand the system and put a higher powered automotive type fuel cell in that'll produce about 75 kilowatts, and that will, with some enhancements in the hydrogen storage system, give us a range of over 500 miles. So this is what's involved in the system. All the basic components, as you can see, it's pretty straightforward and pretty simple. The motor is a brushless DC motor, and that weighs about 80 pounds, and that's coupled to a variable pitch propeller that was made in New Zealand that is a very high efficiency propeller that also gives us the ability to match the torque load of the motor to whatever requirements we have for climb out or cruise. The rest of the components are pretty straightforward. The batteries we're using now are nickel metal hydride batteries that came out of my Toyota Prius, which I was a little upset when I came in one day and discovered the students had taken those out, but they were pretty anxious to get the plane flying. And actually the batteries have worked out pretty good, though. And then the fuel cell is a custom system using a whole new concept where we got rid of the bipolar plates to get the weight down and to improve the efficiency. We have a very large cross-sectional area. Unfortunately, there's a lot of proprietary aspects of that, so I can't show you too much more about that until the patent work is finished. But we're basically using oxygen that we take directly out of the air, and because this is so efficient, we don't need a normal compressor, which normally consumes a lot of your power from your fuel cell, just to get enough air in and enough pressure to cover the pressure drop across the stack. But we are using high-pressure hydrogen already in a tank at about 5,000 psi in a special composite tank. So the real challenge that we have, as I said earlier, the energy challenge here to make this effective is that, as I said, we can cruise along real nicely on only 25 kilowatts of power, which if you convert that at 746 watts per horsepower, that's going to be somewhere in the 35 horsepower area. So if we're going to fly 300 miles, which is kind of an average trip for a small plane, we're going to need 75 kilowatt hours of energy. Now, if we were to use batteries to produce that, as you can see, with lead-acid batteries, it would take 3,000 kilograms. And for our little plane, that would be sure that we would stay very well implanted on the runway. With nickel metal hydrides, batteries which are twice the energy density of lead acids, it would still require 1,500 kilograms. That's why our range is only 25 miles, and that's with about 300 pounds of batteries. And with lithium-ion batteries, which are our most advanced batteries today, it would still take 500 kilograms of batteries to be able to fly for 300 miles. So that's why you haven't seen too many electric-powered airplanes. Now, with the fuel cell system, we have a very, very high energy density for several reasons. Number one, the conversion efficiency of fuel cells is over 50%, where a typical internal combustion engine is about 20%. But we also have the ability today to make lighter and lighter stacks. Matter of fact, I just happen to have here, and I don't know whether, probably can't see that too well. I'll get back in light with it. This is, oops, all right. This is one of the most advanced fuel cells available today, and that is a 100-watt proton-exchange membrane stack that produces 12 volts of power at about 8 to 10 amps. And this is being designed, I hope we can say, for some military applications, I guess, at this point. But the ironic thing here is that the balance of plant, or the other components required to operate this, are actually bigger than the stack. So the cooling system, the heat exchange system, and the support system for getting the air in there, the blowers and so on, are actually bigger than the stack. This only weighs about 7 or 8 ounces. So this is kind of the state of the art. And that's actually being developed right here in Massachusetts by Protonics Corporation out in Marlborough area. So anyway, just to compare, though, even the bottom line, though, we're doing very good, as you can see, on overall energy density and weight with a 150 kilogram total system. And the plane has, that's just about what our allowance is. Still, compared to gasoline, we're not as efficient. And a gasoline engine, even though we only convert about 20% of the energy that's available in gas, the energy potential is over 25,000 watt hours in a kilogram of gas. Where our best batteries, we get no more than 300 watt-hours per kilogram. And with a fuel cell system, including the total weight of all the components, and the weight of the hydrogen, actually, as you can see, isn't much. We only need 4 kilograms of hydrogen to fly 300 miles, and that gives us a little reserve even. So the secret really is how can we figure out better ways to get the total system weight down and how to store the hydrogen. So again, we're using fuel cells because of the efficiency, and you've seen every major automotive manufacturer has a fuel cell powered car under test. Most of those are out in Santa Barbara, California in the Fuel Cell Partnership Program, and a number of them are in Europe. And we actually have a number of fuel cell powered buses in daily use in cities around the country, and there are about 60 that are going into use in Europe this year. And again, the only byproduct that we have is water vapor. There's no odors or fumes. And hydrogen fuel, of course, the nice thing about hydrogen is most people think that we use it up. But ironically enough, it's totally sustainable. We get all the hydrogen back as water. So unlike gasoline, when you burn a gallon of gas in your car, you produce all kinds of byproducts and nitrous oxide and produce carbon monoxide and carbon dioxide, but you can't put those all back together and get a gallon of gas back. But with the hydrogen, it's totally sustainable and renewable. So it's mainly an energy carrier, or a way for us to, move energy in and out of a system. The same things that Ravi had just explained in terms of the overall issues for fuel cells become even more compounded when you try and put it into an aircraft because the weight becomes a very critical issue, where on a terrestrial application, particularly residential and for automobile applications, it's not as critical. But the support components, particularly the efficiency of the balance of plant, the compressor in particular, in many cases that can take up to 20% of the total energy of your output of your fuel cell just to run the blowers, the pumps, and the cooling loop and everything else. And again, the heat transfer, whatever we don't produce as energy comes out as heat. So with your car, you've got, though you're producing 80% heat, just like with an incandescent light bulb, they make a much better heater than they do a light source, but you've got all that extra heat to get rid of. And in a fuel cell, we don't have a high temperature like you do with your exhaust. So we have what's called low-grade heat that we have to get rid of. So it takes a little bit more work. And then obviously the other issues on safety and financial limitations have been a little bit of a challenge because we're building basically $1 million version of a $100,000 airplane. The same airplane that we're using, if you were to go and buy it and equip it with everything that you would want to have in it today, even a ballistic recovery parachute system wouldn't cost you more than $100,000. But by the time we're done, fortunately, NASA is funding about half of the cost of the fuel cell development, and all the other components have been donated. The airframe that we use was donated by DynAero Corporation in France through their American distributor, American Giles Aircraft, and this is the highest performing two-place all-carbon airplane. Very efficient airplane, and also we have special wings that we put on it, so we have a very low stall speed. So we have a very wide operating band, and it's very safe. And the electric motor, though we don't need anywhere near that power, it'll produce a peak power of 100 horsepower. And right now we have about 5 kilowatt hours of nickel metal hydride batteries producing a voltage of 277 volts, very similar to what the bus voltage is of the Toyota Prius. Except we have about 3 to 4 times as many batteries for total energy. So these are the goals of our first flight, and actually I think probably the most important thing is that we make it around the pattern at the airport and get it back on the ground again safely. But then we hope to use the airplane as an educational vehicle and take it all around the country and ultimately all around the world and use it to educate people on the benefits of moving into hydrogen-based fuel cell power systems. We have 10 different teams at WPI that do the bulk of the work on the project, and each team has both volunteers to help work with the project that are outside individuals. Some of them are actually WPI graduates as well, and we have student coordinators, and each team works independently, but we get together periodically to check on the progress. And we do have a lab at WPI in Higgins Laboratory for those of you who get over and visit, as well as a lab at Advanced Technology Products, which is the NASA contract grantee doing the fuel cell research. and also at the Worcester Airport. So this has actually led to some pretty interesting events. These are actually some other students that have worked with us, and they're working on some of the work over in England with the Boeing fuel cell project. They won a design award contest with NASA last summer, and that's our plane on display at the Oshkosh Air Show up in Wisconsin. Just to show you real quickly, this is one of the students working on disassembling the pack out of my Toyota Prius in the left-hand picture and reassembling that into two packs on the right that are what the size that go into the airplane. And they start out at about 117 pounds as the packs come out of the Prius, and they end up being about 45 pounds each, or two of those, 90 pounds equals the same energy as the 117-pound raw pack. We get rid of a lot of weight and get rid of a lot of steel in there. This is the motor mount, which the students have designed, and actually I think one of the volunteers who has been working with them is here tonight. And this is their raw initial sketch of what had to be accomplished to get two battery packs in the nose on top of the motor controller with the motor, and the motor actually is about 11 inches in diameter and just under 9 inches deep. But that is connected directly to the propeller. But they had to do a lot of analysis work for stress and loading to figure out how to use the minimum amount of steel and how to be sure that the strength was proper in all areas and could handle the torque loads. The electric motor actually produces more torque than the gasoline engine that otherwise would have powered the airplane. The propeller adapter, unfortunately, you can't see a lot of the parts there. This is the first version. We now have moved on to a second generation version that has about 9 parts in it. And this has provided a few challenges for some of the machining in the latest design, but we're very close to getting that completed. And you can see the propeller is right at the left-hand side is the spinner of the prop and the motor on the right. And the data acquisition system, the students have done an unbelievable job here. What we had to do is solve a problem with the FAA to show the pilot the amount of fuel remaining on board. And this is one of the requirements that they have, that we have to also try and minimize the amount of switches and controls and elements that could distract the pilot. So we had to come up with a way to show them how much energy was in each battery bank and the fuel cell system as well, and also the amount of time he had in his flight and the amount of time that he might have remaining if everything went well. We still have to provide a reserve for what we call a missed approach, which around the Worcester Airport sometimes is a deer on the runway. So we have to also be careful that the pilot doesn't accidentally hit the wrong button. One of the earlier Air Force tests, this proved, and those are actually the cars underneath of the bystanders there, and he's about 300 feet off the ground, and that didn't turn out to be the best move to make at that time. So overall, what we're hoping to do is to encourage more people to pursue careers in science and technology while educating the public on the benefits and the future of fuel cells. Our test pilots hope to break records, and they're all cowboys. Hoot Gibson, our chief test pilot, was the head of the Top Gun school with the Navy out in California, and then went on to become an astronaut, flew 5 missions, and then became the head of the NASA astronaut program. And even while he was flying as an astronaut, he broke records by finding new ways to creatively take the existing records, like the highest sustained flight, horizontal flight, while he was taking the Russian astronauts to the Mir. So he's looking forward to breaking a lot of records. But we hope to have a lot of fun with this. And we also have a couple other projects underway I'll just tell you about for a second. We're building a demonstration system with a 3-kilowatt fuel cell, and this is going to be such that we can take that out and jointly with DOE and other groups use that to show people a real live fuel cell that has enough power to run the average home. And that's going to be about 3.5 feet long and about 1.5 feet high. You see it sitting on a normal desk there, and that's almost done. And another project that we had done earlier with some students was building the first fuel cell powered entry in the American Tour de Sol race with the Northeast Sustainable Energy Association. And we hope to actually put another entry into that this year, which is actually a little neighborhood vehicle that Chrysler donated to us. And this is actually like a real fancy golf cart. I think the president actually is even using one of these now. It's a very nice little rig and fully covered. And we're going to put a 3 kilowatt fuel cell system on that over the next month. And this is what the system looks like, which is similar to what you saw earlier. And actually, that's the stack. And the stack, of course, is the main heart of the system. And that's about 16 inches long and about 9 inches in each dimension as far as left and right. And those are on the end of, actually, the tie bars are one of the major elements of weight. This is the tie bar, or I mean the end plates. The tie bars connect the two end plates together, and then we have springs to maintain tension on it. On this particular unit, we have, I'm trying to remember the final count, I think we have 40 individual cells in this, and that nets us out around 24 to 27 volts. And then we run that through an up converter to end up with 72 volts. So anyway, we hope you'll join the project if you're interested, and you can stop down later and talk to us and help to make this a reality. And we're always looking for volunteers, and our website is Aviation Tomorrow if anyone wants to, check our progress and see what's going on.
Thank you, Jim. Thanks, Jim. Thanks, Ravi. Thanks, Ed. If I could have Ed and Ravi come on up here. I hope you've followed my instructions and thought up some really interesting questions, because we've got 3 people here who know an awful lot about this stuff, and they'd like nothing better than to chat with you. The museum folks have some microphones, so if you just kind of put your hand up, they'll give you a microphone and you can ask away.
Hi. Rather than about the technical aspects of this, the catalysts, platinum and palladium you're speaking of, I know they're both expensive and fairly hard to get. If you ramp up production of all these, will you be able to get it, and at what price?
I think that's a very good question that I don't think we know the final answer to. But for example, the platinum is used in automobile converters. All automobiles have platinum at the exhaust, and that's recycled. And I think it's the same idea for fuel cells, that even though you would use platinum in fuel cells, that you're not going to throw it away, but that would be recycled. And it's easy to recover. It's not very hard to recover.
Thank you very much. For the production of hydrogen from natural gas, you said you need steam. What is the source of the steam, and what is likely to be the energy and carbon contribution as a result of having to create steam? Or will that be a self-sustaining process once it gets going?
The steam, just water. That's what you need.
The source
You
of
mean
heat,
to heat the steam. Yeah, well, I didn't put all the other things. You can do the heat management. So part of the heat you can use the combustion of a methane.
That's
you can
waste
use
heat.
that. Waste heat. You can use that to heat the steam. To heat
How
it.
much in terms of the ratio of 1 to 4? What happens to that ratio?
You mean the steam to methane ratio?
You do the whole process, yeah. What's the
About 3 to 1, depends on the.
You seem to have focused on PEM fuel cells and a particular reformer. There are lots of fuel cells and lots of reformers. Why those two, and to the exclusion of
I can talk about the PEM fuel cells. As you rightly say, there are all kinds of fuel cells, and they are known by the type of electrolyte. You have an alkaline fuel cell, molten carbonate fuel cell, solid oxide fuel cells. These are all different types of fuel cells with different applications. For example, the alkaline fuel cell is really suitable only for space applications, because if you have any carbon dioxide which you have in the atmosphere, the alkali electrolyte carbonates, and eventually it would stop working. Similarly, the solid oxide fuel cells work at very high temperature. Molten carbonate fuel cells also work at very high temperatures. And these are typically molten carbonate fuel cells are for utility applications. So this was just an introductory presentation on what's a fuel cell, and I decided to focus on PEM fuel cells, which is what is most interesting right now for automobile and for personal applications.
Where are we going to sequester all the carbon dioxide?
Well, carbon dioxide, you want to answer that, Brian?
Yeah. Current thought is you put, there are different ways to do that. One of them, you can use that as a tertiary oil recovery. It's pump the car because that we're going deeper and deeper to the oil well, so we need to get the pump pressure. So you can pump the carbon dioxide to the oil field and push the oil up so the carbon dioxide will stay in there. The other suggestion is to put in a deep sea ocean to sequestrate it. And then also you can use that carbon dioxide for certain applications. Dry ice is one of them. And there are also some research going on, what we call dry reforming of carbon dioxide, by combining carbon dioxide with methane to form hydrogen. So that's another.
There's no easy solution. That is the
Yes, sir.
Yes. A year or two.
We can get one more there. Yes, sir. We'll take him first. Who had the microphone?
Right here.
Okay.
A year or two ago, there were some articles in the technical and scientific magazines about small appliances like laptops and cell phones using borax as sort of the sustainable fuel for fuel cell powered devices. Can you say a bit about where that is?
Yeah. Basically, they were using sodium borohydride, not borax itself, and they produced a borate byproduct, which is in the borax family. Sodium borohydride offers a lot of interesting potential because it can be kept as a dry, stable powder for a long period of time. And when reacted with almost any noble metal, they usually use ruthenium, it'll give off hydrogen very readily. And all you have to do is mix the borohydride with water. Millennium Cell Corporation is actually the leader in that field of producing systems, but it's still a little unclear exactly how that whole process is going to work. It does generate a lot of heat in the catalytic reaction, and you do need a lot of water. And actually, you pretty much use all the water the fuel cell can give off just to mix with the borohydride mixture. But that is coming along with lithium hydride and magnesium hydride. There's a lot of hydrides that would all do the same thing.
Well, it still seems to me that fuel cells, the way you've presented them, are elegant, but still at an intermediate step, and ultimately you're depending on fossil fuels to generate the electricity to produce the hydrogen or the reforming. What is going to happen when we run out of oil and run out of natural gas? Will alternative sources such as wind power, geothermal, and solar energy be enough to initiate a true hydrogen economy?
I can take a shot at it. It's a real problem. We use too much energy, and we've used most of the reserves of the fossil fuels in the last 100 years or so. All that a fuel cell does is it increases the efficiency with which the energy of the fossil fuels is converted into electricity. So you would use maybe only half as much fossil fuel for a certain amount of electricity that you're producing compared to a conventional production. So that's one advantage. The other, and I should say, is that eventually we will have to wean ourselves off of fossil fuels, and it's in principle that's not so hard to do, because what you can do is you can use biomass that is presumably replenished. So you burn it or you use it in a manner that produces carbon dioxide, but that's fixed again next year in next year's crop. But you can use ethanol to produce hydrogen. It works like a charm. You don't have to use fossil fuels. You can use renewable or biomass-based fuels for producing hydrogen.
Yeah, and just one step further, although we ultimately hope that we have enough wind power or solar power, we still don't always have that at the exact moment that you need it as far as the production time versus the utilization time. So converting it even electrolytically, which isn't as efficient as other processes, into hydrogen and oxygen, and then recombining those when we do need it with a fuel cell, still gives you an overall higher turnaround efficiency. And there you have no CO2 produced, and there's no hydrocarbons involved at all.
We're up here in the back left corner up here, I think.
Yes. One of the terms I heard, and only once, was the term safety. With a potential explosive mixture in the vehicle, how safe is it?
Okay, you're talking about the safety of hydrogen. Well, hydrogen actually, has anyone ever heard, by the way, of a hydrogen fire or a hydrogen explosion? Unlike every day, there's never a day that we don't hear of a house being blown up with a gas leak. Has anyone ever heard of a hydrogen fire or explosion? Yes, sir. The Challenger. Okay, that was a little different situation, but it did involve hydrogen. Okay, that's good. Okay, there have not been that many, and people think normally of the Hindenburg, which of course had nothing to do with the hydrogen. That was the coating on the skin of the balloon that held the hydrogen in. Had the hydrogen exploded or even ignited, there would have been a hell of an explosion. Hydrogen, because of the energy content, obviously is an explosive gas and has to be treated with the same respect and courtesy. And one interesting aspect is a hydrogen flame does not produce a visible flame. There's very little visible light to the human eye, and though with an infrared detector or other thermal detectors we can see a hydrogen flame, but if properly cared for and properly treated and stored, it can be a very safe fuel. One of the concerns that we have had is what is the best way to store hydrogen and transport it, because the amount of energy you have to put in, for instance, to transport it as liquid hydrogen is usually more than you get back out when you gasify it and use the hydrogen in a fuel cell. Yes, sir.
The viability of hydrogen as a fuel seems apparent and has been around with us for a long time, I think. But I wonder if you would comment somewhat on the storage problems that we have, which is, in my way of thinking, the real problem here, particularly when it comes to automobiles and the great infrastructure, gasoline stations, and how all of a sudden we manage to get hydrogen into that loop.
Yeah, the infrastructure and the whole network of having hydrogen available is a major issue that still confronts us, particularly on the automotive side. For the home, most of the fuel cell systems that are going into homes at the rate of about 5 a day right now, and even more in Japan, rely on compressed natural gas and a reformer that they strip the hydrogen out of the CNG. But as far as how we deal with hydrogen, we did a study with the number of students at WPI last year looking at every possible way to source hydrogen and store hydrogen and what was the most efficient and the densest liquid to store it in. And does anyone here want to venture a guess what that was? Besides water, because water is obviously there, but the amount of energy required to get the hydrogen back is pretty high. It was actually ammonia, NH3. NH3 has the highest density of hydrogen, both as a liquid and it's even higher actual net hydrogen than liquid hydrogen. Though liquid hydrogen does achieve a higher overall density, but the amount of energy that it takes to liquefy hydrogen versus what you get back is quite low. But ammonia, which can be produced from urea, which is a very dry, safe pellet used in the farming industry, and of course ammonia by itself, anhydrous liquid ammonia is used very commonly too. And that, although it will combust ultimately by producing hydrogen if you heat it up enough, by itself is considered non-flammable by the Department of Transportation. So there are a lot of different answers, but I don't think we have begun to solve that yet. And as far as the automobile applications go, we may move ahead far enough with direct methanol fuel cells improve the efficiency, reduce the crossover, and solve some of the problems. With a direct methanol fuel cell, you don't need to have a reformer. You mix the methanol directly with the water, and that's what's being used in these small systems. Even Protonics makes a similar cell to this that will run directly on methanol, and it only takes between 3 and 5% methanol. The rest is water, and you just recirculate that water over and over again.
Okay.
Also, the way to, not necessarily you have to store hydrogen. You can have onboard generation of hydrogen. In other words, that's why the oil companies have so much interest, is that you can directly reform gasoline and use the hydrogen as the hydrogen source for your fuel cell.
I'm going to ask you if you would indulge us, and anybody that has questions left, come on up. Ravi, Ed, and Jim would love to discuss those questions with you, and we're going to let the rest of the audience go. It's getting late. I want to say thanks to the museum. This has been a wonderful series. Thank you so much. And let's thank our speakers one more time.